Okay. In our previous class, we talked about we tried to solve the equation of motion of the manual because of the spin transfer torque. So in a spin transfer torque, there are two kinds of contribution. One is called the adiabatic, the other one is non-adiabatic torque. So because of these two torque, which one is the orthogonal, this torque give some torque direction to the perpendicular to the M and the round M, round X. And the other one is give the torque in other perpendicular directions. So based on the previous method, we tried to find the spin tensor torque by the adiabatic term, and we found this contribution. And here, the round M, round Y means we are talking about now we are working on the nanowire direction of the Y direction. So current is flowing to the Y plus Y or minus Y direction. So this is the direction of the domain or variation. So when you're taking the round Y, we can, using the chain rule, we can take the round M, round theta, and round theta, round Y. And here the round theta, round Y can be obtained from the definition of the domain world. This is the domain world structure as a function of the Y. So when you're taking the tangent in both sides, you can obtain these relations and taking the integral to the Y direction. So when you do some simple math, we can obtain the round Y, round theta round Y, give us sine theta over delta. So here is the result. Actually, I didn't mention about this relation in the previous lecture. Okay, and the M vector is actually ms r hat. So we can taking the integral, the derivative to the r hat to the respect of theta. So this term gives us the theta hat as you see here. So you can check it by yourself. Finally, we can obtain the adiabatic torque by the spin tensor torque of the direction of the theta hat. Okay, so theta hat actually give in this coordinate system, theta direction means this direction. Okay. So please remember that part. And in a non-adiabatic torque, we obtained phi hat. So non-adiabatic torque acting on this direction. So actually for the M, the R direction torque doesn't do anything. So actually any torque can be mapped by this theta and phi term. And adiabatic torque give a theta term and non-adiabatic torque give a phi term. So based on this two torque, we can rewrite the equation of motion of the theta dot and phi dot with these two additional terms to the domain or torque on with the field. This one is done in a previous lecture. Okay, so this coupled differential equation can be solved by introducing simple matrix. So now let's introduce the K domain world again, which one is already I mentioned when we talk about the field-driven domain world motion. So it's quite similar to the field-driven one. So we can obtain these relations, and then finally we obtain these coupled equations. Okay, so here we assume the non-adiabatic torque is proportional to the adiabatic torque by the beta. So when zero field and the zero non-adiabatic contribution case, we obtained these relations, and you have to pay attention. These two mathematical expressions are identical. So that means when theta hat is 0, theta dot is 0, q dot is also 0. So there is no domain motion anymore when they satisfy this relation. So that's what we call the intrinsic pinning effect. But if we have a non-adiabatic torque, non-zero non-adiabatic torque, these two equations are the same. So when they satisfy this condition, this term is not zero. So when they satisfy this condition, means this is going to zero, or phi dot is zero case. So when I'm talking about the steady state case, Q dot is expressed in this form, and when we simplify it and take some approximation when alpha is smaller than 1, then the domain wall velocity is proportional to the Bj, the density. Actually, this is the velocity representation by the velocity for the current density, and the proportional ratio is beta of alpha. So please remember that in a domain wall motion by the field, we have this expression, and this is quite similar because the Bj itself is the velocity unit, and alpha, beta is the dimensionless. So the velocity should be expressed by the proportionality to the Bj, and this proportional constant is beta of alpha. And when beta is zero, we obtain the previous result again. And this result is valid only when this relation means in this relation, the sine to phi should be smaller than 1. So we can simply obtain this relation. So when Bj, the current density, is smaller than this one, we can obtain the steady state domain wall motion. And in a precession domain wall motion, we taking the time average, which one is the phi is varying, so we can taking just time average and drop it. After we drop it, we can obtain Q dot by when you combine these two equations, we can obtain the average velocity is just proportional to the Bj. Sorry. Yeah, please remember that the steady state case, they have this relation. And Q dot at the field driven motion, we have this form. So when actually I already mentioned gamma H0 is order of 10 gigahertz and delta is order of a few nanometer. So we can obtain when alpha is 0.01, which is a typical value, we can obtain the order of meter per sec. But in the steady state case, in this relation, we have alpha is in a denominator, which is 001, and beta is the value is order of alpha. Beta is order of alpha. So actually, nobody knows exact value of beta, and it's very difficult to measure the beta. But anyway, there is some chance the steady state domain motion is faster than the precession motion. Okay, and here, as we already mentioned for the Bj, Bj is the velocity, and this is proportional to the drift velocity of the electron. And for the moderate current density, like this case, the velocity is very, very small. In other words, to achieve the fast domain motion, we need a very huge current density. That's the limitation of this technology. We have to reduce this current. Okay, so this is the simulation result. Are you guys, can you see the motion of domain wall here? This is micromatic simulations. So as you see here, domain itself is moving very steady motion. I apply this amount of current. And this is the snapshot at 0 nanosec and 1 nanosec, 2 nanosec. The domain wall motion has some displacement. And as you see here, domain wall structure itself is very stable. They are not changing the shape. So this is corresponding to the steady motion of the domain wall. Okay. And this is the result of this simulation as a unit of time and the position. So this is quite linear, as you see here. And if you're taking the slope of this linear motion, we can obtain the velocity. So here, this is 10 nanosec. We have here, it's about 800 something nanometer divided by 10 nanometer. We obtained 8 meter per sec. Yeah. In this simulation, I put this relation, this constant, and here this value is corresponding to 25 meter per sec. So we obtained around 140 meter per sec by this relation. But here, okay, in this calculation, I used the spin polarization of p-value is 0.56, and the j of corresponding j for this one is about 50 meter. So we can obtain this 25 meter per sec for this one. This result is a little bit overestimate this micromax simulation result, but still it's not bad. They can predict the order of 100%. And in a precession domain wall motion case, look at this simulation here. The difference thing is the domain wall stay at the same position because I made some options. Always the domain wall can be positioned at the center. Actually, this domain wall is moving now, but I changed the frame of the simulation to keep the domain wall at the center. See, there is some change of the domain wall structure here. This is because of the precession of domain wall. See here, the color is changed means the direction of the manipulation is changed. And then again, so this is a snapshot at 0.5 nanosec and 1 nanosec. And as you see here, domain wall structure is not that simple. There is some kind of more structure in a domain wall compared to the previous case. In the previous case, it's very simple. They are heading to this direction, simply. But here, there is some fine structure inside of the domain wall. And they changed also. So because of the large current, they are larger than the worker breakdown. So we obtained very large the variation of domain wall. And in this case, I applied this amount of current density, which one is corresponding. Sorry, maybe this is correct one. Sorry, this is incorrect. So corresponding BJ is 560 meter per sec, and this is the result. we simulate the 10 nanosec and the position vector. Yeah, there is some kind of fluctuation of the velocity. Please remember that when we calculate the velocity, we take in the time average, because actually this precession, the dip means the change of the structure of the domain wall. So they increase the velocity, but sometimes they are moving backside and then moving again. So this is the position vector. So when we think about this part, domain wall velocity itself can be negative even in small region. But overall behavior of domain wall motion is the linear velocity, constant velocity. So here, this value is about 4,500 meter something to the 10 nanosecond. So you can obtain this value. And compared to our prediction, it's not that bad. Okay. So as I already mentioned, the domain wall can be moved by the spin transfer torque. So we can make domain wall motion devices. Okay. Actually, this is the last page for the spin transfer torque domain wall motion. So it's a good time to get some questions. Any questions? Okay, so if there's no more questions, then let me keep going. Actually, this domain velocity is quite good. As we already mentioned, the order of 100 meter per sec is we can make a good and fast enough devices. But unfortunately, this current density is too large. With this kind of large current density, the nanowire easily burned out. And the energy consumption is also very large. So we have to reduce the current density. But as we already mentioned, this is the domain velocity is proportional to the current density. And if we reduce the current density, we can obtain the smaller velocity. What's the solution? Okay, people try to find a way to improve the domain wall velocity by increasing the beta term and many tries. But sometimes people found domain wall is moving to the direction of the electron flow. But sometimes they found domain wall is moving to the current direction, which one is the opposite direction of the electron flow, and this is not understandable for the based on the spin transfer torque. So people investigate more, and they found in a ferromatic layer and the heavy metal structure, there can be additional torque. That's what we call the spin orbit torque. Because this heavy metal is a large atomic number, there is a strong spin orbit coupling. I typically say the spin orbit coupling is proportional to the horsepower of the atomic number. So as the atomic number is larger, then we have a strong spin orbit interaction. So they found this spin orbit torque can play a very important role in a domain wall dynamics. And this spin orbit torque is there are many kinds of spin orbit torques. The most important thing is spin pad and Rashby pad and the DMI, the short of the Jaloshinsky-Moria interaction. These three terms are very important in modern spintronics. So I'm gonna briefly explain what's the meaning of the spin-orbit path and the Rashba path and the DMI. Okay. Then first, let me briefly explain what is the interaction. Spin-orbit interaction means actually they play a very important role in many phenomena in ferromagnetism, like magnetic anisotropy and magneto-optical effect, anomalous MR, and also spinor MR, spinor effect, damping, and many plays. And what is the spin-orbit interaction? Let's think about this case. We have a nuclei here with a positive charge, and electron is moving. This is our frame. When you're taking a look at the atom, they behave like this. But let's think about that. This is, let's say, Earth, and this is the Sun. When you guys taking a look at the Sun in the Earth, on the Earth, the Sun is moving. Earth is not moving. So in our frame, Sun is moving, and we are in a constant position. It's same for the electron. In the viewpoint of the electron or frame of the electron, those nuclei is moving. So there's some motion of positive charge around themselves. So this positive charge motion can generate magnetic field, right? So this electron feels some kind of a magnetic field because of this motion. So this motion is actually reciprocal motion of their motion itself. So the angular momentum of electron is similar to the angular momentum of the nuclei in the frame of the electron. So this motion generates kind of a magnetic field. So we can say this part is the magnetic field because of this angular momentum. So this is the nothing else but the Zeeman energy term interaction by the spin and the field. Okay, so that means this term play like an effective field to the electron. So we have an interaction between L and S. L is the orbital and S is the spin. So that's what we call spin-orbit coupling. And as you see here, we have a speed of velocity, speed of the light. So that means this effect is relativistic effect. And also, this potential gradient is important. Means if there is no potential gradient, then this spin-orbit coupling going to zero. So the essential ingredient is the angular momentum and the potential gradient. In many 3D transition metals, the net angular momentum is zero because of the crystal field, symmetry of the crystal field, the angular momentum can be cancelled out. So the effect of the spin-orbit interaction in a 3D metal is very small and usually ignorable. However, in a heavy metal, we have a large angular momentum, and this angular momentum is not compensated in a metallic system. So when we have a heavy metal, always we have a spin-orbit coupling. So because of this spin-orbit coupling, there is some kind of torque can be arised by the interaction between the spin and orbital. And the Rashba path is exactly came from this spin-orbit coupling. Just to think about that heavy metal and the ferromagnetic layer structure. the electron passing through this interface. Let's think about the potential across this direction. There is some atomic potential in a ferromagnet, and there is a atomic potential in a heavy metal. And generally they cannot be same, so there is some kind of a step. So that means the round V, round R is finite, give a finite value at the interface. So this large Y path is purely interface path. And in this expression, we can say the large field, which one is corresponding to this part, is can be expressed this form here. So you can easily think about that. This part, mu0 ms, when you multiply this term, we obtained, always obtained the energy per volume. So the remaining part must be the energy per volume. And that alpha is called the Rashba coefficient, is the kind of material parameter with the unit of the energy per energy meter. So anyway, so this is the material parameter, and they including all these terms. So here we just think about the direction of this large path, because the spin angular momentum in this case and the direction of the spin is determined by the conduction current here. So this gradient gives us the direction of the G, this direction, and this is the current flow. Okay, and this is the spin polarization. And anyway, with these two terms, we can obtain the direction of the X, and we can obtain the magnitude of H large bar. That means, yeah, it's including many complex physics, but in short, there is some kind of effective field at the interface to the direction of the X direction here, which one is perpendicular to the current direction and the gradient of the potential, or the thickness direction of the your multi-layer system. So with this field, this ferromagnetic magnetization in the ferromagnetic layer feels some kind of torque. Yeah, there is some kind of motion of this spin because of this field. Okay. There is some kind of torque and cross H should be. So this torque, this field can be added to the precision torque, but the direction of the field is always pointing the x-axis, and depends on the current direction. This can be plus or minus x direction. So generally, we have a transverse direction effective field at the interface because of this large Y path. You know, there is some spinori path. Actually, we already mentioned it. Spinori path means there is some kind of electron bending. It's quite similar to the ordinary Hori path, but without any magnetic field or magnetic material. You know, pure non-magnetic metals. There is some kind of two bendings for the, for example, the spin up and spin down can be separate because of the attraction inside of these non-magnetic materials. The origin of a spinori path is quite complex, and there is many kind of possible reasons. If we have a symmetry breaking in a crystal structure, there is some possibility of the intrinsic spinal effect, or there is some kind of infinity, we have a skew scattering, and or the side jump effect. So anyway, this kind of spinal effect widely observed in heavy metals like platinum, tungsten, or gold and palladium. So anyway, when the current is flowing this direction, the y direction, there is a kind of two current, two spin current. One is the heading in this cross-section view. If current is coming out in this screen, we have a spin current in this direction, or maybe the other direction. That means the spin polarized electron is moving to upward or downward with this polarization. So we have a kind of a spin current to this interface. So it's quite similar that the spin transfer torque. Spin transfer torque is we are sending some kind of spin polarized current to the ferromagnetic layer, and by the angular momentum conservation, there is a torque in the ferromagnetic layer. So the same thing happens. In this sectional view, in this cross-sectional view, the current is, current is actually in this upward direction in the screen. And the spin current is up or down, upward or down with the different spin polarization. So this blue one means the spin current from the heavy metal. And this spin current, and this is the ferromagnetic layer magnetization direction, there is torque between two of them. And this torque is actually quite similar to the spin transfer torque, which one we already learned. Here the P is the polarization direction, so here we have a, let's say, minus X. And G, the M is the direction of this magnetization, so we have a plus G, something like that. And this term gives us Y direction. And this is given us again the X direction. So the torque acting on this configuration, we have a torque of the X direction. Maybe the sign can be wrong, plus or minus X direction. Anyway, so in that means to generate such kind of a torque, we have a such this direction of the field. So don't confuse the field and the torque. They are always orthogonal. Please remember that the torque is M cross H. Okay. So this torque means if we have some kind of torque existing, that means we have such kind of effective field, which one is orthogonal to the M and the torque. So as a result, we have a effective torque or effective field to this direction. Here, this direction is actually the direction of the current, so Y direction. So spinal effect generate a kind of a field to the direction of the longitudinal one, the direction of the current. But because of this spinal effect, we have a spin current to about the direction. And this torque I calculate here is correspond to the adiabatic torque. But we have always non-adiabatic contribution, and which one is perpendicular to the adiabatic one. So we have a transverse term can be exist, but usually it's not that large. But anyway, they also play very important role. So we call this is the field-like term. Yeah, this field like means non-adiabatic one. They are depends on the society. People like the field like term or non-adiabatic term. But anyway, in all sums, by the current with the heavy metal, we have a two kind of torque called the rush bypass or spinal pad. But because of this rush bypass, we have also longitudinal term from the rush bar contribution. And for the spinal pad, they are mainly damping like term or Slonczewski like term. This means the STT term. Anyway, so mainly the transverse direction, the contributions came from the rush bypass, but always we have a spinal pad also. And in a longitudinal direction, to this direction, we have a spinal pad field, or there's some rush bar contribution. But generally, those two terms, it's not easy to distinguish. So when the experimentalists say, we just said the longitudinal term and the transverse term, but we don't know which one is came from the rush bar or spinal pad. They can be coexist always. So usually each contribution are mixed, and it's not easy to distinguish both contribution. But anyway, those two talks, those two effective fields play a very important role in the domain motion. Okay. And I just explained the spinal pad and the rush pad. So we have a very important additional energy called the Jaroszewski-Moria interaction. In short, we call the DMI. Okay, just to think about that. The energy of the interaction between two spins, these are energy expression, and they are scalar term. The energy should be scalar term. And we have two spins, and they are vector. So generally, to generate scalar term from the two vectors, we need a kind of second rank tensor between them. And this second rank tensor can be divided by the diagonal term and the symmetric term, the antisymmetric term. Then this symmetric antisymmetric term can be obtained by this simple relation. So this kind of expression is very general. In many cases, crystal structure has a symmetry. So this asymmetry part, antisymmetry part, will be disappeared generally. But sometimes, if we have a symmetry breaking, this antisymmetry part can be survived. And this symmetry part gives us the Heisenberg exchange coupling. So they have just a simple inner product. But this antisymmetric exchange interaction gives us those kind of terms. So in this case, the two vector make another vector by the cross product, and we need the additional vector to generate the scalar energy. So this kind of energy can be arisen by the symmetry breaking of the system, because this antisymmetry part must be survived by the symmetry breaking. Then what's the meaning of this energy? Okay, so let's think about this Heisenberg interaction. In this case, we already know this inner product means they like a parallel or anti-parallel depends on the sign of J. So they make a collinear configuration of the monetization. Okay. They prefer the aligned spins. But in this case, this term gives us sine theta. Here we have a cosine theta. So that means if we have a certain sign of D value here and assume the direction of this D vector is parallel to this cross product, then this sine theta must be 1 or minus 1 to maximize or minimize, minimize the energy of the this interaction. So the theta should be pi over 2. So DMI preferred the perpendicular spin configurations. So what can be happens? This DMI existing always with this exchange term. So they prefer the parallel configuration, but they prefer the perpendicular configuration. They compete each other. And as a result, we have a kind of non-collinear spin configuration. So that means in a fermat layer, if we ignore the domain structure, all spin direction must be parallel. In an antiparallel layer, they must be antiparallel. But with this DMI, the spin configuration can be more complex. They can form the spiral structure and helical structure and many more. Okay, and also in a domain world, for example, here, if we have one spin here, depends on the sign of D. Next spin preferred this direction or this direction. So that means the neighboring spins preferred this direction or the rotation of this direction or the other direction, called the chirality. So the important thing is in a domain motion, this preferred chirality can be suppressed the work breakdown. Please remember that work breakdown, after the work breakdown, the domain velocity is just proportional to the Bj. But before the work breakdown, we have this expression, and this can be larger. Okay. Also, because of this DMI, we can make some kind of non-collinear spin structure, and we can form a very important spin structure called the skirmion. We're gonna explain the skirmion later. Okay, and let's focus on the domain structure first. This is the formation of 3 domains: up, down, up, and we have 2 domain worlds here. And this graph tells us the direction of the monetization. And from the 0, we have find a certain angle in a domain world. And finally, they have a 180 degree. And then here. But let's see the chirality of the domain world. They are rotating this direction, right? But here we have a opposite direction of the domain world. Means the slope of this part are different. The sign of slope are opposite. Okay, so we have 2 opposite chirality here. And then when we apply magnet field, this magnet domain wall can be easily rotated to this direction. And then they can be easily removed. And let's think about that. The other case, we have a same 3 domains and 2 domain walls. And the difference is we have a same chirality. Here, domain wall is moving to this direction, and those parts are not the same. They just beside of this pin, they prefer this direction, while they prefer this direction. And in this case, because of the DMI, without DMI, this structure and this structure and this domain wall are exactly same energy. But with the DMI, they prefer, let's say, this kind of orientation. Then this pin must be this direction. They cannot be this direction. So this pin and this pin has a different energy. So with the DMI sign, they prefer this direction. So with the DMI, the domain wall structure preferred always same chirality. Then when we apply the external magnetic field again, this term rotating to this way, this way, this way. So that means this domain wall can be extended, and this domain can be shrink down. But here, there's a rotation of this way because of these pins. Then this top also easily remove the expand this domain. However, at the end of this shrink down of domain wall, this pin wanna moving to this direction, but this pin moving to this direction. So at the center, this pin cannot be rotated. So that means they are much more stable compared to previous case. So that's what we call topologically protected. Yeah. So because of this topological protection, the domain wall motion is affected by the suppression of the work breakdown. Usually, after the work breakdown, domain wall can be deformed. Then they require more energy. So that's why there is some kind of a velocity drop. There is many energy loss. So by the suppression of the domain, the work breakdown, we can make the faster domain wall motion. So equation of domain wall motion, which one is we already did in our previous case. There is the spin transfer torque term and the field term and the anisotropy term, the domain wall anisotropy term here. Which one? So far, this part is we already learned. And if we have a general case, x, y, and x direction of field, but there is some kind of additional contribution by the spinor effect and the DMI effect. So in this equation, you can easily see the DMI is play with the x field direction of the x, and also here. So we cannot distinguish the DMI field and the x direction field. And also the spinor effect is acting to the y direction, but there's some alpha here. So DMI is we can make enhance or suppress the impact of the DMI by applying the direction, the excitation field. Sorry, here the excitation is the field direction, and then the current direction, or wire direction. In our previous case, current is following the flowing to the y-axis, but now the coordinate system is changed. I'm sorry, because I'm taking the from the another reference. So anyway, the DMI, we can easily see the role of the DMI. The DMI is acting like the longitudinal field. But in a the spinal effect is a little bit more complex because of this alpha. In this equation, this is maybe Q dot. Spinal effect is scaled down by the alpha compared to the y component. But here, spinal effect torque, the field is much larger than this the transverse field. So it's more important role here. So anyway, you can easily found. I'm sorry. So because of these two effective field, domainal motion can be easily changed. Or without spin transfer torque, domainal can be moved. Okay. So in this sense, we can easily imagine the role of DMI. They acting like the excitational field. So see here, the domain is now below time. But with this directional field, they can form this direction. So they prefer the nil type domain with the same chirality. So this DMI combined with the spinal effect, this is the spinal effect, the spin injection from the heavy metal layer. Then there is some torque to this domainal magnetization direction. So we can easily move the domainal by combination of the DMI and the spinal effect together. And also, the work breakdown is determined by HK. The domainal anisotropy means the energy difference between the below wall and the nil wall. But because this DMI prefer making the energy difference to the nil wall, so they always prefer the nil wall. So the domainal anisotropy can be increased effectively. This term can be effectively increased by the DMI. Okay, so they prefer the nil wall and increase the work breakdown field or the work breakdown current. As a result, domain will be more effectively moved. So as you see here, in a zero DMI, the work breakdown can be easily obtained with a small field, and then domain is moving like this. But with when you increase the DMI energy, the work breakdown can be increased. So in this case, we can achieve a much faster domainal motion compared to the zero DMI case. Okay. DMI play a very important role in the domainal dynamics, and you can obtain high domainal velocity with the DMI. And also, DMI play a very important role in a spin structure. The squamion is kind of a quasi-particle came from the particle physics. But in magnetism, we call this fermions those kind of spin structure. Just imagine the all spin is pointing to outside in a 3D structure, or they make such kind of a chiral structure. And if we map this three-dimensional structure to the two-dimension, we can obtain such a spin structure. This is 2D, 3D, and this is 1D structure. And in a 1D structure, which one is consist by 3-domain structure with the 2-domain walls with the same chirality. So in this structure is what we call the fermion. And this kind of fermion can be formed because of the DMI. And what's the importance of this fermion? This fermion size is can be very small, like order of 10 nanometer. And they are very stable because they are topologically protected. That means they cannot be destroyed easily. Also, that means when we give us some kind of perturbation, the structure is not disturbed. So the small deformation gave a very flat potential change. So when they are moving, if we have some kind of obstacles, they are not pinned. They just bypass the obstacles. So they can be easily moving with the small field or current. That means we can sending some information with the fermion. So that's what we call the information carrier. So this fermion has a very strong advantage. They are small and stable and easy moving, and that means they can be good candidate for the information carrier. So what's the meaning of the topologically protected one? So you may heard about the topology in mathematics. The donut can be deformed to the curve. So there is some photo I took from the internet to a topologist. This curve is same to the donut. In a topologist, the sphere are not the same the torus or the two torus, but this donut and the curve has the same topology. So when we deform this donut to the curve or the other way, there is no violation of the topology. But from the sphere to the torus, we need some kind of a breakdown of the, we should make the hole. So they are not topologically the same. So the topological number must be conserved. So when we form the fermion, they have some topological number, and to control that kind of number, we need many energies. So that's why the fermion must be stable. So there's many ideas using the fermions. So that's what we call the fermionics. So here the fermion can be moving, and like here we have a motion of fermion like a racetrack. They are moving together, and they can bypass the obstacles, and they can moving very consistently. Actually, this is the simulation. So that means we can sending the fermion or information with very small current. Here the current density is much smaller than, actually this is the 10 ampere per square. This is quite smaller than the domain wall motion. So there is some kind of idea of the kind of transistor using the fermion. So there are many brilliant ideas with the fermion to making such kind of information devices. Okay, So this is the brief introduction of the Chun-Yeol, and today I explained about the domain motion by the spin transfer torque and the spin orbit torque also. And actually there is a much more complex physics behind the spin orbit torque and the domain motion by the spin orbit torque, but I don't want to give that details to the student. Okay, so next class, the Wednesday, I'll give a last lecture about this semester by introducing some kind of future of the spintronics. And yeah, actually this is the last lecture with many mathematics. Fortunately, on Wednesday, I'll give a very brief introduction of the future of the spintronics. So yeah, don't worry about that part. Okay, so I think it is time for the questions. Please ask me questions about this domain. Okay. So topological protection is here is a good example. Here, if we have in this case, the chirality of these two domain are opposite. And when we apply the external field, this domain wall is moving this way and this one is this way. So that means this domain is extended easily. And this one is this domain can be shrunk down with this external magnetic field. And let's focus on these two spins. This spin is moving to this direction by this external field. And this spin is moving to this direction. And they are also. So all these spins are finally pointing up by rotating this way. So they can be easily removed. This domain can be easily removed. But let's focus on this spin and this spin again. Here, this spin is moving this way, and this spin moving to this way. Okay. Then what happens to here? Those motion are opposite. So this spin is cannot move to either way. So to remove these spins, we need extra energy. This is what we call the topological protection. Actually, in a mathematical concept, topological protection means they cannot be changed from one topological state to the other state, but without a breakdown of the topology. But in physics, topological protection means kind of additional energy barrier. They can be overcome by supplying the enough large energy, but they require additional energy. So that means they are stable. So in a mathematician, the topological protection means it is impossible to change one topological number to the other one without any topological number breakdown. But in a physicist, this kind of barrier cannot be infinite energy. They have a kind of finite energy barrier. So don't be afraid. This topological protection means there is some additional energy barrier for the simple case. Okay, in the 10th question, okay, the Chun-Yeol velocity is determined by the Chun-Yeol itself and the external field or external current. But in a nanotrack, there is called the edge effect. So the existence of edge affects the domain, the common motion. So your question, in short answer is yes, they affected by the nanowire width. But it's not very simple. It's very complicated relation. Okay. So any other questions? Okay. So let's back to our previous one. So work breakdown means here, when they satisfy this relation, the field is smaller than this one. The domain motion is steady motion. When external field is larger than this one, the work breakdown can be happens. Then what's the meaning of this term? This is the energy difference to the, so we have a domain wire, the nanowire here, and let's say up domain and down domain here. Domain wall can be this way or this way. And which one is energetically preferred? This term, the NX is this direction. I'm sorry, this one. And NY is this one. So this term actually give us the energy difference of these two domain walls. This is the nil type and blue type. So generally, this term is always came from the geometrical effect. The energy difference came purely the geometrical effect. But with the DMI, we have a effective field for this X direction. So because of DMI, domain wall preferred this one. Means the energy difference, the nil type and the blue type can be larger. So to overcome this domain wall anisotropy, we need more external field or external current. Okay. Changgang, that's a good question. Let's back to here. In this equation, you can see the effect of spin transfer torque and effect of the spinol effect and the DMI. So in generally, in heavy metal system, this structure, the contribution of STT usually not very efficient. And as you already see, this spin transfer torque required very large current density to obtain certain amount of the domain velocity. And also DMI making the domain wall prefer the nil type. That's the important role of the DMI. And this spinol effect is very effective to the nil type domain wall only. So by combination of the DMI and the spinol effect, we believe we can obtain the very effective domain wall motion. That's my answer. Okay, any other questions? Okay, today after this class, I upload this lecture note, and also I upload the rest homework. Okay. Okay, then let me close this lecture here and see you Wednesday morning. Okay, bye.